All right, it's 2 o'clock on the nose, so go ahead and get started. Hey, everybody, my name is Jamie Gray. I'm with GPI Geospatial, and I'm going to be talking to you guys about SLAM technology, particularly for indoor mapping, and where some of this emerging technology falls into place with this whole sort of concept or notion that people are calling the Metaverse these days. So just an overview of the presentation, I'm mainly going to be focusing on the fundamentals of what SLAM is, how it works, key differences between this type of LiDAR and other types that are out there. Then we'll talk about a little bit about what this Metaverse notion is and how us as geospatial professionals are going to play a pretty key role in whatever that ends up being whenever people kind of decide and figure it out. And I believe that this type of technology is going to, sort of help build the framework for some existing conditions for indoor mapping. I'll talk a little bit about the hardware that we went with at GPI. There's lots of different flavors of SLAM-based scannings. There's small ones, handheld ones, backpacks. The one that we have, you kind of wear it on your shoulders and on the front. So this is not a sales pitch for that by any means, but that's just the particular one that we decided to go with. And I have the scanner with me, so I'm going to be scanning the exhibit hall during the social, so come by and say hey or check out the technology itself here in a little bit, and then tomorrow I'll have a data set. You can stop by our booth and check it out if you want to. And then if we have time, we'll talk a little bit about accuracy assessments of the data set compared to other LiDAR technologies. So I've only got 20 minutes. I might talk a little bit fast to kind of get through it, but here we go. So just an intro to GPI Geospatial, in case any of you are not familiar with us. We are a subsidiary of Greenman Peterson Incorporated, a large engineering firm, mainly based along the East Coast, but within geospatial, we're about 150 strong. We do lots of LiDAR work, lots of aerial work, UAV work, static scanning. We do a lot of surveying, GIS. So kind of that whole discipline of geospatial services we do under our group. In North Carolina, we are here. We have offices in Raleigh and Wilmington, and we just signed a lease on one in Raleigh, so we've got a Raleigh office. It's not my basement, basically. It's where I've been working for the past couple of years, working from home. So we're excited to be in Raleigh. So I always use my why is this important pitch when I'm talking to people, who cares about SLAM? What is it? Why is it interesting? Why are we all sitting in this room? We took 30 minutes out of our lives to learn a little bit more about it. I would say that, if I was to sum it up, what's one of the most exciting things for me personally about this technology is just the speed at which you can collect very rich 3D data sets. Imagery, LiDAR, the whole 9 yards. We're consistently seeing that it's roughly 10 times as fast as it would be if we were using a static scanner on a tripod going from setup to setup. Just to kind of give you an idea, I should be able to make the rounds and scan that whole exhibit hall in probably 10 to 15 minutes max for that whole space. So we can scan 150 to 200,000 square foot of indoor space per day using this technology. So that's the exciting thing. It's opened up a lot of doors for prohibitively expensive scanning projects and efforts that we can take care of in a fraction of the amount of time just by adopting this type of technology. And then geospatial data is a fundamental component. I've said before, and I do believe that as we move forward, and if this whole metaverse thing happens, we're talking about digital twins, and we've got a lot of buzzwords around that we're trying to figure out what they mean, and we're starting to see what they look like in practice. And us as geospatial professionals in general, I believe it's an exciting time to be in the business that we're in, and a lot of possibilities to help us fulfill this concept in the future. So SLAM is actually an acronym. I'm going to spend quite a bit of time kind of unpacking this slide here. It's an acronym that stands for Simultaneous Localization and Mapping. And simultaneous, you can also think about that as real time. And the localization part is where you are with the scanner in terms of the environment around you. It determines your location there. And mapping, which is mapping the unknown environment. And my background is as a land surveyor. I became that first and got into all this other fun stuff later. But the localization part, that's sort of been the key. As a surveyor, we think about that as our ground control. That's where we start. We start with the localization. We know where we are. We are very interested in where we are, horizontally and vertically. So we start from that vantage point, and we map the environment around us. So we start with the localization comes first, then we do the mapping from there. But this whole SLAM concept sort of flips the script on that, in that basically the localization is unknown. We start with mapping the environment happens first. That doesn't happen second. So the mapping happens, and then the localization happens after that in relationship to the environment that gets mapped first. So, it really should be in the real order of operations of things. It's actually simultaneous mapping and localization. But I guess SLAM sounds a lot cooler than SMAL if you wanted to use the acronym the way that it actually does. But the mapping comes first, and then you get localized. So it's the complete opposite of what how we approach mapping projects. So it's a system. There's a lot of things going on at the same time with these systems, and it starts with sensors. We've got LiDAR sensors. Some of them are photo or video based without LiDAR. That's kind of our first component is the sensors. And then, the sensors are operating, they're continuously collecting data. And then behind the scenes, there's a feature matching algorithm that happens to where it's mapping all this data in real time. You get millions and millions of survey points. And once you get all that data, the feature matching starts picking out areas like flat plains or corners or things that it recognizes and starts to sort of, what's the word I'm looking for? It starts to comprehend the environment around you. It starts picking out the walls, the corners, the doorways, the furniture. So all that stuff is happening. And then after that, the pose estimation starts happening in that, it's doing this feature matching continuously. It recognizes this table right here, for example. It's like, okay, this is a table right here, this is the top, this is the sides. And then once I move over here, for an example, it's still matching those features, and it recognizes that that's the same table as it was when I was standing over here. It's still matching up all the features, and that's how it knows that I moved over here, because it's seeing and recognizing that those same features, and just from a different vantage point. So once it starts figuring out the environment and it starts recognizing all these different vantage points in the same features over and over again, that's how it knows where I am when I start walking through the space. So when you're collecting the data itself, you do a series of interconnected loop closures. So it kind of looks like you're a drunken sailor walking around in circles, kind of overlap in the areas from here to there, and that's how it starts to account for accumulated errors, things of that nature, where it has to go back and it recognizes, hey, I've been here before. This is where I was when I came from this direction, and then I've looped back on myself and I'm here, and it can start dealing with the errors, and then it does, a least squares bundle adjustment over the whole thing on the back end. So it uses those interconnected loops to help solve those errors and model those out. So that's kind of a flow chart of sort of what's going on behind the scenes. It's all happening in real time. It's pretty cool to watch. Like with the unit we have, I describe it as you're basically painting the room with a big can of blue spray paint. With the blue spray paint as the point. So you can see in real time, it starts building the environment out. You can start seeing all the walls and doors and features and stuff around you. It's all stitching all that data together in real time. So it's pretty cool to watch when it's actually collecting the data. So SLAM is not really too new. It sort of came out of the robotics industry in the early 1990s, where they had, some robots or autonomous vehicles that were, they had to go into an environment that they didn't know, and they had to kind of figure out where everything was and its relationship to the world around it. That's kind of where it all started. But kind of a combination of a lot of smart people working behind the scenes on some of these algorithms and solutions to the SLAM problem, and computing power getting a lot stronger and a lot smaller. It's kind of caught up to our surveying and mapping industry, and we've got our own application for it, which is indoor mapping in particular, and also outdoors. But if you think about your Roomba, if you have a Roomba at home, or if you've got, like Paul drives a Tesla or whatever, it's using SLAM technology in those devices to where it's, and there's some UAV platforms that use it for obstacle avoidance, things of that nature. So it's getting to be pretty ubiquitous in several other things. This is just kind of how us as geospatial providers have learned to embrace the technology and use it for our own purposes. Just a couple of key differences. So, we've had aerial LiDAR for a long time. Static scanning has been around. Mobile LiDAR has been around 10 to 15 years. So LiDAR is not really new. We've got this is just a different version of it. But one interesting thing about this and why it's so good for indoor mapping is that it doesn't have GPS. It's not a component. It's, the SLAM technology takes care of that localization. You're not using your GNSS to localize the aircraft or your mobile LiDAR vehicle or your static scanner. The SLAM technology is doing that localization itself. So we don't need GPS, so we can, map indoors. It's a lot faster, like I said, a lot simpler on the back end for processing the data sets with it. A lot faster. It's a viable alternative to tripod-based LiDAR or static scanning, things of that nature. So just to kind of, I'm not going to go too deep into this metaverse concept because it really is just kind of a concept at this point. So the basic concept is that a metaverse would be kind of a digital copy of the real world. And as opposed to us humans walking around in the real world, that we would be, avatars walking around in this metaverse world. And, it's got some pretty interesting implications, even from, design and construction that we deal with a lot, to where, you can test out your design in the metaverse first before you build it in the real world and kind of solve all those problems ahead of time in this metaverse environment. And then, it allows people to have more rich or meaningful real-time interactions across distances. It opens up a lot of, breaks down a lot of barriers, whether they're, geographical barriers or political barriers or whatever. And then, like I mentioned, sustainable design is important. Um, and, they even talk about, like digital stores. You would go into the metaverse, you'd put your goggles on, you'd walk around and you would do your shopping in the metaverse kind of thing. I know that there's some, I can't remember the name of the automotive manufacturer, but they're kind of going down that road to having their showrooms in VR and sort of testing out this metaverse concept when it comes to even just retail shopping. But the catch for this metaverse thing is that to create a digital copy of our existing as-built world, I mean, how's that going to happen, and who's going to do that work? You can't really just do it all, on the desktop, so to speak. If we wanted to do a digital twin metaverse of this conference center, we could take a SLAM type scanner, we could scan all these rooms, we could get all the detail, we can get all the rendering for stuff, and basically recreate a hyper realistic version of this whole conference center, for example, would be, and people are doing that with on the building level, but so yeah, kind of that base map, if you will, of the existing conditions for something like the metaverse. There would need to be a lot of indoor mapping that would need to happen to stand that up. So I personally believe that that the SLAM-based technology for scanning indoors is it's definitely a step in that direction for sure. And then kind of where's the geospatial data fit in? The metaverse is going to be a location. We always talk about location. That's kind of the key. That's the type of intelligence that GIS professionals and others we bring the where to all the other information that we have. And plus somebody's got to attribute all this stuff, and it's not just a matter of having the the existing conditions in kind of a cool map or immersive environment. It's got to have some sort of intelligence to it as well to make it meaningful and useful. So I think that there's going to be a large GIS component to this whole notion with moving forward, with making it into something that's useful to people. So got a few more minutes. I'll just kind of jump right into the hardware for the so a German manufacturer we went with is called Navis. It's a very interesting piece of equipment for sure. You've got a LiDAR scanner above your head that's oriented in a horizontal direction, and then you have another LiDAR at the chest level that's oriented in a vertical direction. So the idea is that you've got your horizontal and vertical LiDAR collection happening to give as close as possible as a 3D floor-to-ceiling data collection, and then right below the LiDAR above your head is 4 20-megapixel cameras that capture panoramic 3D imagery. This is kind of the upper left is a field of view for the LiDAR sensors, the horizontal and vertical orientations, and then the imagery front to back and side to side. So you're getting 360-degree coverage, especially with the imagery. But you can kind of notice that there's a sort of a blind spot behind you with the LiDAR, but that gets taken care of by if you're walking into a corner, you just have to kind of turn around and make sure you get, you kind of fill in that blind spot with the data collection. So that's a picture of me actually wearing the scanner at one of our facilities, and you'll see me walking around with it this afternoon if you're going to be at the social. You get a lot of really weird looks if you're walking down the street wearing one of those. We did a city block at downtown Charlotte recently, and I'm just looking at the display the whole time if I'm using it, but people that are with me, they're like, yeah, you should have seen some of these weird looks that you got walking down the street with it. But probably the most humorous thing that's happened to me with this, there was a gentleman who saw me scanning an area, and he thought that I had like a spinal injury, that I was wearing like a headgear thing, and he was like, "Yeah, I saw you," and I was like, "Oh man, that poor guy. I wonder what happened to him." But it was just the scanner was all that it was on that. So you definitely get some interesting looks. People want to take your picture, all kinds of stuff. So anyway, so it's definitely a unique piece of equipment. Just real quick, before we went with this particular solution, we scanned one of our offices with this unit, and then we also scanned it with a super high dollar static laser scanner, like a P40. And what we found was, we did we pulled some distances between the two data sets just to kind of get an idea of relative accuracies. And I mean, it's negligible. It's in the hundredths or thousandths of a foot difference between these elevations. So it's definitely for indoor mapping, architectural type elements. It's definitely repeatable with existing technology that we could just do a lot faster. And it's just a couple of examples of that. We're working on, I say we, I mean, I am trying to work on our own white paper for accuracy comparisons, but Navis had published one that we've used for a reference before. And with that, pretty much right on time, that is it for me. And I think we've got a few minutes for questions if anybody has any. Yeah, that's kind of all in with everything, because there is a pretty robust software platform, cloud-based software platform that Navis offers. That was another thing that we liked about that platform. So, kind of the hardware, the software, the training, and all that, all the stuff rolled into one. It was just right about what Paul said. And that. Yep. So once you get done with a data set, we mentioned kind of in this slide in the beginning, this bundle adjustment step that happens. That's a big part of what happens on the back end. So once we're done with a project, we download a copy to our laptop, and then we upload it to the cloud server that Navis has, and it does a lot of the crunching on the data. It deals with the panoramic photos. It kind of works all that stuff out in the cloud, and then it sends you an email when the data set is done. You go up and you go through a couple of more steps. But you can bring down the data to your machine if you wanted to use, another software package, or if you wanted to bring it into your GIS or AutoCAD or MicroStation or whatever. You can bring the LiDAR data set down and work with it with other third-party. But even just the cloud solution by itself, it builds you kind of a basic BIM model that you can go through the space and do asset management and tag all the attributes, the entryways and exits and that kind of stuff, even just within that platform. But you can also export it out and deal with it in several other third-party applications with it.
So, in comparison to Metaverse, I know it's the same basic model. So, how many scans would you have to take for different? How many have different vantage points, whatever? And so, what is like the turnaround time for per scan?
Yeah. So the recommendation with this one is that you scan continuously. I just walk around this room. I'm scanning the whole time. I'm not having to stop and start or anything. So they recommend that you scan no more than 45 minutes per session. That kind of keeps the data set manageable, and it takes care of if you get any kind of drift or anything in your path. And so if the space is big enough, you have those like 45-minute chunks of data. And then on the cloud side, you actually register those data sets together and get one unified data set out of it. But turnaround time, the biggest thing that takes time is dealing with the photographs. But I could scan, like we'll scan the exhibit hall and upload it later tonight, and then I'll have the data set for people to check out in the morning. So it's pretty quick to scan, process, and stand up a data set through the cloud. And that's where the data set lives there. You can interact with the data, you can make measurements, you can do whatever just in the cloud if you want to, or you can pull it down to your local machine and deal with it that way.
Since you had mentioned that the metaverse is still largely just a concept,
Mm-hmm.
what are some of the applications of SLAM technology that you're used so far?
Yeah, so I think that where we are right now, it's really kind of feeding into this digital twin notion to where you've got a building, you could basically have a metaverse of like one building, which would be a digital twin. I think that's, pretty much what they mean when they refer to that. So if you get all the existing conditions, you get into a model, if you've got like IoT sensors throughout the space monitoring, whether it's HVAC or other platforms, you can tie that into a building management system to where you're getting the health readout from your sensors, but you also know exactly where that particular sensor is inside your space. You can go into your building model and say, hey, this is the sensor, getting a weird reading on sensor XYZ. Where is sensor XYZ? So you can go into this digital twin or building model and say, oh, yeah, that's the one right over here, and send somebody to that. That's where the location part is important to where, because we do get a lot of data from sensors, but the whole thing of like putting that particular sensor in a particular part of a particular building in a particular space is kind of that's sort of where we're at right now with, so it's kind of like the building level metaverse kind of things is where we're at, so, yeah. Anybody else?
You talked about localization, SLAM algorithm, but how do you tie that, when you talk about that localization happening to, say, survey grid after the fact, how does that process take place?
Okay, yeah, that's a good question. I didn't really have time to jump into it, but yeah, you can tie these data sets as you're collecting them if you do have survey control. You don't have to have survey control, but if you do, there's a way to, you actually take the scanner off and you physically occupy the control point and log it into the data set. And then if you have XYZ coordinates on those points and you just feed it a CSV file, you have to give it a point ID when you collect it in the field. On the back end, it says this is point one has XYZ coordinates, whatever. This is where it is in the data set where we logged it in there. And it uses that data, uses that survey control to basically georeference everything, bring it up to a datum, to where that way you can just like bring it straight into your GIS and it'll just come right in where it needs to. So, so survey control is definitely an important piece of it if that's part of the plan, but you don't have to have it if you don't really need it either. Yeah. All right. Well, thank y'all for listening to me ramble on for 20 minutes or so. I love talking about this kind of stuff, so be happy to show you the scanner later. Just stop by our booth if you want to talk more. Be happy to. So thanks again.